get started. And to begin with, I would like to introduce myself. My name is Claudia Vasquez. I am the ASME Vice Chair of the Southern Alberta Section. And the agenda for today is as follows. We will start with welcome and introduction of our guest speaker. Then for about 20 to 25 minutes, Grant will give his presentation about proton technologies. Then we will have 20 minutes for Q&A, and we will wrap up with some final remarks and other section logistics. Before I get started, I would like to launch a poll to know a little bit better our audience. So you will see on your screen just two questions. We want to find out how did you hear about this event, and if you believe hydrogen can be part of Alberta's energy future. If you can please respond, we will share the results right after. Chris, did we get enough responses yet? Thank you. Well, Grant, you have a very positive audience, which is a great start, I believe. So with that, I'm gonna introduce our guest speaker today. Grant Strem is the chairman and CEO of Proton Technologies Canada. Grant was born and raised in Calgary. He has a Bachelor in Science in Geology and a Master in Science in Reservoir Characterization, both from the University of Calgary. Grant considers himself an explorationist and has worked for various producers, including Paramount Burlington Resources, ConocoPhillips, Total EP, and Husky. Grant also worked as a reserves evaluator for GLJ Petroleum Consultants and as a research analyst at TD Securities covering the oil sands sector. He also started his own oil company focused on light oil, helium, and geothermal resources. In 2015, Grant co-founded Proton Technologies with Dr. Ian Gates, who then was department head of the Petroleum and Chemical Engineering faculty at the University of Calgary, as well as Grant's former professor. 6 years later, the company is stronger than ever. Grant believes it is possible to produce zero emissions hydrogen at far lower cost per joule of energy than diesel and gasoline. Without further ado, I pass it on to Grant. Welcome, Grant.
Thank you very much, Claudia, and thank you for the kind introduction. I was, based on the poll, where 96% of the people who responded said that they believe hydrogen will be a part of Alberta's energy future. I hope to just give you my flavor on that. I'm very happy to see that this is already understood that to decarbonize our energy system, well, hydrogen needs to play at least some portion of the role. I think it'll be a dominant role. Opinions vary on how that looks and how much. And in my opinion, it mostly comes down to price. How do we drive the cost down for making hydrogen the most? Yeah, so without further conversation, let me share my screen and begin my presentation. Okay, can everybody see? Maybe one of the hosts, if you could say yes. Great, okay. So when I think about energy technologies, if the goal is to try and move towards clean energy, there are really a few metrics that I think are important. Low cost, as I mentioned. Sometimes I use the analogy of the transition from whale oil to kerosene. So people used to burn whale oil in their lamps, and they didn't switch to kerosene because everybody loved whales, just kerosene was lower cost. So if you're at the grocery store looking at lamps and whale oil costs 10 times as much as the kerosene lamp oil, well, that's an easy economic decision. So I think this transition towards clean energy is the same. There's been my whole life and longer significant environmental concerns that have been fairly well communicated and well studied. Some of them have been fixed, but generally, if the fix did not involve a cost drop, the problem remained. So now I think a lot of environmental challenges today are related to air. Well, one of my big issues is air pollution. And I think to make significant improvements on air pollution, we have to have alternatives that are more compelling and more attractive than burning hydrocarbons. And hydrogen fits that role, especially using these fuel cell for transportation and hydrogen compatible turbines. Eventually, I guess, without going too much in the weeds, it can be done even without making nitrous oxides. The carbon intensity is something that I think is going to be a growing part of our discussion through time. So maybe somewhat analogous to organic foods. So it used to be that an apple that wasn't sprayed with pesticides was more likely to be small and expensive and less appealing. Now it's fairly mainstream to have organic products at very comparable costs, perhaps in some cases less expensive. Carbon intensity is something that hydrogen in particular, is going to be measured against. So this is by life cycle analysis. So even something that does not have direct carbon involvement, such as wind and solar to electrolysis, there's no carbon emissions once it's up and running. But if you look at the structure, the amount of steel in the ground and concrete and transporting, building foundations, the electrical power lines, the new roads, the access routes, all of these factor into the life cycle analysis measurement of carbon intensity. So if you assume your windmill is going to last 25 years, then you can divide up all of that carbon footprint across 25 years, plus maybe something for disposal of it afterwards or replacement or upgrades. So there's a carbon intensity measurement metric that goes with all of these. And if there's a way to make massively carbon negative hydrogen, I think that this is all going to be tracked and equalized by others in blockchain. And that's through, fairly advanced conversations of what's already happening in Europe and Asia. So when people are comparing these different colors of hydrogen, well, at the end of the day, it really doesn't matter what the color is exactly. It's more about what is the carbon intensity. So that is a metric that will be, I think, third parties will be assigning. Somebody will do a study of your process and see what all the various inputs and factors are associated with your design and assign a carbon intensity score to your hydrogen. And then that gets tracked, and that will flow through to goods such as groceries, such as commercial goods. This shirt, I don't know what the carbon intensity of this shirt is, but I'm pretty sure it got here with some sort of carbon-based fuel transporting it from whatever country it was made in. So there will be as governments like to do, one of the things that's easy to tax is carbon. So if they're already doing this, so goods from Australia to the European Union have a carbon tariff just because Australia does not have a carbon tax yet. And I think that will be an increasing limitation on exports of various goods and to try and further reduce this. So carbon intensity of even final goods will include analysis of the energy, but it starts with analysis of the energy. The other one that I like to point out is, maybe 6 or 8 months ago, there was all these pictures of, maybe a year ago, vast solar panel fields in the deserts of Oman and in China and places like that. And people said, wow, look at all this solar power we can build. But you don't see those pictures anymore because people are getting nervous and upset about the ecological footprint of new disturbances. And that's not just the new power lines and the roads that go in, but actually, there can be a significant ecological disturbance, especially with wind and solar on a massive scale in a new area. I'm a big fan of solar on existing infrastructure, but definitely if you're doing it in some fragile grassland or some desert somewhere where there's some rare lizard or something, that's going to upset a lot of people too. So that has to be considered. And I like our process because it doesn't create or require a new ecological disturbance. We use the same footprint as an existing disturbance. Our process, for those who are unaware in general, works like this. Everybody knows that oil has a lot of energy stored in it. We turn different types, we separate out different types of oil like diesel and gasoline and jet fuel and kerosene and various products that when we oxidize them in an engine later or in a turbine later, give us a tremendous amount of exothermic energy. It releases a huge amount of heat, and that's what drives pistons, spins turbines. There's a lot of trapped chemical energy within oil. But in an oil field, it's just this raw, crude nature. And if you oxidize it there instead of an engine, you don't need as specialized as a receptacle. You don't need to do all the pre-processing and refining. You can just inject oxygen into it, and every type of hydrocarbon will react with pure oxygen. So it doesn't really matter what grade the oil is. The main thing is just that you have a sufficient seal or cap rock that there's no chance of basically escaping CO2 back to the surface. So anyway, the oxygen goes down there. When an oil field gets abandoned or is in late life, it's not abandoned because there's no more oil left in the ground. It's abandoned because it's too expensive or technically infeasible to move the remaining oil molecules to a production wellbore. But there's still, in every case, a lot of oil left in the ground. Maybe with the exception of surface mining, but that's not applicable to our process anyway. So anyways, we go in and try and oxidize all this remaining oil. It might be hard to move a big oil molecule to a production wellbore, but it's really easy to get an oxygen molecule to move around in these systems, and easier still to move hydrogen around. So when these reactions happen, there's a lot of reactions, but the main one initially is oxidation, like in a car engine, or partial oxidation. And that gives you a huge amount of heat for other reactions that produce hydrogen. And then we have a downhole filter for hydrogen that was developed in the steam methane reforming industry in the early days. And we take those and put them down a production wellbore near the top of the reservoir where the gas likes to accumulate above the liquids. And the only thing that can go through these filters is pure hydrogen. So we get this big stream of hydrogen coming to surface. These are two old technologies with a huge industrial base. In oxidizing oil fields has happened more than 500 times around the world, and always there is production of hydrogen as a byproduct. And same thing with the other thing, steam methane reforming filters. These palladium alloys in the early days were designed to be resistant to H2S and designed to be resistant to many other carbon monoxide and anything that might toxify the more common ones that are in use today. So anyway, we use these old-fashioned things combined in a new way. And people say, well, why hasn't this been done if it's so easy? And I think it's like wheels on suitcases. For decades and decades, everyone carried suitcases around, even though everybody knew wheels existed. So after people bought their first suitcase with wheels, they thought, in hindsight, why was I doing this? Hindsight's often 20/20 for very simple ideas like this one. Here's an example of a data set from Canada from the early 80s, where they got up to 40% hydrogen at Marguerite Lake. And I think that if they did this by accident, as a byproduct of an oil operation, it should be replicable if we're intending to optimize for it. And I feel strongly confident that the economics anywhere near what they did in the past will be robust and interesting for hydrogen production. So there's this big move away from carbon today. You know, a lot of people are, well, trying to decarbonize, whether the fear is greenhouse gases, which is, you know, I think most Canadians would rather it be 5 or 10 degrees warmer, but anyway, leave the whole rationale behind, whether your main motivation is air pollution, your main motivation is greenhouse gases, or your main motivation is efficiency, because moving all that carbon around is not efficient. The main point is we have these huge stores of chemical energy all over the place. This one field in Alberta has 2 trillion barrels of oil. So, you know, 2 trillion barrels of oil, and a lot of it is not economic to produce as oil. The definition of economic reserves, I think the last report I saw, there's something like 300 billion barrels of recoverable resource, which means that out of the 2 trillion barrels, a high proportion is expected to be not economically recoverable as oil. So that's where Proton would love to come in and take over parts of the basin that are either late life existing oil projects. Those are preferable because there's so much infrastructure, thermally completed and insulated wells that already exist. You know, the roads, the power lines, the pipelines, they're all there. So if somebody's walking away from a pad, we can come in at that point with our process and turn it into a great big hydrogen production capability. One of the things hydrogen's used for is at refineries, it can upgrade oil, or upgraders, where basically they take hydrogen and get it into these big viscous oil molecules, which shortens the chain length and makes them more useful for things like fuels. So, or even plastics or what have you. So adding hydrogen hugely increases the value of the oil that leaves Alberta. But not only that, you know, one thing that's, I've been saying this for years and I don't know why it doesn't seem to resonate, but when we have diluent that we're importing, like Alberta imports roughly almost 1 million barrels a day just to mix it with the bitumen, so that about 1/3 of the what's called dilbit leaving through these big pipelines is actually diluent that we purchased at a premium to WTI oil price, and we're selling for a much lower price mixed with diluent. So the whole purpose, mixed with bitumen. So the whole purpose is just to be able to flow down pipelines. But if we added hydrogen instead, you know, there's all these big pipeline conversations. We need more pipes, and you know, I'm sure if you live here, you've heard the conversations. But if we just add hydrogen to our own bitumen and upgrade it ourselves, especially if we have a easy co-located abundant source of hydrogen, that gives the opportunity to reverse the import lines for diluent and also adds 1/3 of the exit lines. So if this was done at large scale, through existing pipelines, we could export roughly almost 2 million barrels a day extra of light oil and get a premium to WTI or maybe WTI instead of this discounted product where, you know, they don't really want the diluent at the refineries along the Gulf Coast because there's so much of it nearby in Texas anyway. Anyway, that's kind of just one use case for hydrogen. I think that's not the main use case, but you know, should be part of the conversation at least. One of the things that people don't realize is that it's already cheaper to make hydrogen on a gigajoule basis than diesel and gasoline. So diesel equivalence is approximately $4 a kilogram. If you include the fact that when you burn diesel in an engine, about 80% of the energy is just thermal losses. It goes to waste heat. By contrast with the hydrogen fuel cell, about 65% of those gigajoules of energy go towards turning wheels. So if you switch to a hydrogen fuel cell, big rig or train right now, you save a lot of money on fuel. So hydrogen today is Alberta makes about 5,000 tons a day of what's called gray hydrogen. This is done through steam methane reforming, where they burn a bunch of natural gas and react it with high temperature steam, which they get the steam from burning natural gas. And it goes through together and triggers water gas shift reaction, which is more or less the same chemistry of what we're doing just in the ground. I like gray hydrogen. It's far better than diesel and gasoline. So I'd rather my neighbors be idling their hydrogen fuel cell vehicles, which are basically electric motors with the hydrogen fuel cell as a source for the electricity, rather than idling diesels and loud garbage trucks and buses. And the main filtration for all of that in an urban center is human lungs. And that, of course, has huge health consequences for all of us. But there's talk about what's called blue hydrogen, where you basically try and capture as much of the smokestack emissions as you can from steam methane reforming and inject those into the ground. This has been happening in Canada for about 25 years. And there are many reservoirs that use what's called CO2 enhanced oil recovery. So if you jam a bunch of CO2 into certain oil fields, you can expect a big bump in your production of oil. And typically about 2/3 of that CO2 stays down there. You do get some of it back up with the oil that you re-inject again, and on it goes. So that's called carbon sequestration. And a lot of it turns in, the CO2 will on some time scale naturally become carbonate within the system. There are ways to accelerate that we've patented. While we're on this slide, though, I'll point out that one of the costs for steam methane reforming is they are always buying natural gas. So if you're always buying fuel, that's going to have an obvious effect on your economics. And it's impossible for, on a gigajoule basis, your output of hydrogen to be cheaper than your input of natural gas. So natural gas, if you're just making electricity, for example, it will always be cheaper than hydrogen if your hydrogen source is steam methane reforming. By contrast, if we end up buying some late stage oil field for $1, and believe me, they're out there and they're very large and they're on the wrong side of somebody's balance sheet as an abandonment liability, there's an eagerness to offload those, and they can only do it to credible counterparties. So if somebody with a good balance sheet steps in and says, I'll shoulder this abandonment liability, and then transforms it to a clean energy process like through our method, then basically the fuel's free. We use the ground itself, the oil field itself, as the reaction vessel. So that's a huge amount of capital expense and operating expense savings, because there's no giant construction of the high temperature, high pressure reaction vessels at surface, and all the cooling loops and pipes and maintenance that's required with those. And then we can, using our downhole filter, have the hydrogen in the ground. I'll have to update this. I think lately we've been calling ourselves clear hydrogen because we have a lower carbon intensity than electrolysis from renewables. But anyway, to give you a sense of scale on the cost of hydrogen, it can be way, way, way cheaper. I think in 10 years, people will be commonly fueling up their pickup trucks for like $5 to $10. If we inflation adjust it to today's dollar. Anyways, it's a huge, huge opportunity to save money on energy. And if you can get your cost of hydrogen below the cost of natural gas, then it works great for blending into, heating systems, natural gas turbines, all of that, like base load power. Suddenly you have something that's profitable against natural gas. And as far as I know, our process so far is the only one I've heard of that has a clear path to get cheaper than natural gas for hydrogen. But what we do have to build is an air separation unit. So that works by cooling air to -185 until the oxygen turns to a liquid. Then you've got a vessel full of liquid oxygen. It goes out through a one-way valve, you warm it up, and it provides a tremendous amount of pressure back when you go through that phase change of liquid back to a gas. So the oxygen, as it does that, gives you enough pressure to go down into the ground. And in fact, Our most recent calculations at Proton suggest that we could co-inject at no additional energy expense into our site at Saskatchewan anyway. It depends, it's somewhat dependent on the reservoir pressure of the field, but we can co-inject 2 parts CO2 to 1 part oxygen just with that expansive force off the oxygen. And if we warm it up, further, then we can get to higher pressures or more CO2 or some combination of the both. And there is waste heat because we have to power our air separation unit with something. And turbines that burn pure hydrogen are our intended source for that. So we can use the waste heat from that to get the temperature up quite high to be able to more or less freely inject huge volumes of CO2. So for example, on a 500 ton a day notional hydrogen production project, we have to inject about 6,000 tons a day of oxygen, but we can drag along about 12,000 tons a day of CO2 into the same reservoir, just using that expansive force of the oxygen. So from a carbon sequestration point of view, that's far less expensive than trying to do a standalone CO2 compressor. So far, that's the scheme that I've seen most commonly done and talked about in terms of blue hydrogen. But definitely if you are doing our process anyway, freely injecting the CO2 is an advantage economically. There are thousands of reactions that happen in the ground. There's interactions with the mineralogy of the rocks. There's interactions with the various fluids that are down there. There's sulfur in the system that's burning, like H2S makes sulfur dioxide. All of these different components, it's a complex system. So if I had to summarize it into some main reactions, the initial oxidations release a huge amount of heat that gives us and provides some chemistry. So carbon monoxide, for example, is a feedstock to water gas shift. Gasification also provides carbon monoxide and hydrogen. But I think the main and most important reaction is water gas shift, which is you can only trigger it below a certain temperature. So that's why you don't get it in coal gasification projects so much. In those, it's higher temperature. The reason it's higher temperature is because in an oil field, 2/3 or more of the system is just rock. So you're constantly heating up rock as you go. This equation here is called water gas shift. Carbon monoxide and steam reversibly change to CO2 and hydrogen. So the CO2 forms carbonic acid. It forms carbonate rock within the reservoir. And we're constantly pulling hydrogen out through the filter. In an equilibrium reaction, if you're constantly removing ingredients from one side of the equation, then it rebalances towards the missing ingredients. So the more hydrogen we pull from the system, the more the system gives us. That's a big advantage on our efficiency, and one of the reasons that our patent is, I guess, kind of interesting because it takes advantage of this chemical reaction. Some parts of the world, like Iceland, have rock types that very quickly trigger carbonate formation. We might not have that type of system in all of our oil fields here, but we do have a lot of wastewater and raw sewage and ion-rich waste streams all across our society. I think boiler blowdown from steam generators is the most readily available and proximal source of very, very low cost dissolved ions that can quickly precipitate carbonates. So that's basically the goal, is to try and accelerate the formation of carbonates, because it's the volume difference between solid carbon storage and gaseous carbon storage is tremendous. Many fields, it would never be a problem, especially if there's a giant water lag. But in some cases, it is a problem. So whether it's a CO2 sequestration project or whether it's our type of project, we have ways to accelerate the deposition of carbonate. So here's what in general, a typical oil field might look like. Ours has 200 million barrels left in place, so that's what I use the math for. If we know that if we want the lifetime of the project to be supplying hydrogen for 50 years, then we know stoichiometrically, how much it takes. About 3.42 kilograms of oxygen to react 1 kilogram of oil stoichiometrically. So if you know how much oil you have and you want to react it all in 50 years, then you know how much oxygen you need. That works out to about 6,000 tons a day of oxygen in the case of our field, which we predict will give us approximately 500 tons per day of hydrogen. Porosity is somewhat important. So within beach sand, for example, you might have 30 or 35% just empty gaps between the grains of sand. And if in the case here, we have 30%, which if we just warm up this entire system using the specific heat capacity of silica, water, and oil, just to warm the system from 25 Celsius to 300, about 9% of that thermal energy just goes towards heating the system. So you can see that it's more efficient in systems where there's more porosity and relatively less rock. So if you're in a tight rock where there's 10% porosity, then 27% of your thermal energy just goes towards heating rock and heating the container. And I think the economic limit will be approximately 5% porosity. We'll know more about it as we build out at scale and test different types of reservoirs, which is our plan. So our goal for Proton Canada is to take about 10% of the resource in Western Canada and use our process on it. And we think that's enough to supply at steady state 10% of the world's 2040 energy needs, total energy needs, heating, electricity, everything, transport fuel. So that is a vast goal, and how do we do that? Well, the math shows, about 10% of the oil resource is going to be needed in Western Canada. And then we'll need about 17 million tons a day of oxygen, which is like 1,700, 10,000 ton a day oxygen plants. So just to give you a sense of scale, we need to build a lot of air separation units, and we'll need a whole supply chain on that and assembly line of a modular system that we can build these out. So that gives us 19 years left. I'll be 60 years old, but I think, just the resource we have here allows us to be in Western Canada an absolute clean energy superpower. I want to see that happen. I think that it's appropriate that we use our resources in the best way possible for stimulating our economy and solving some problems in the world. For me, like I mentioned, air pollution is a significant one that this addresses very, very nicely and works well with sort of the global mandates towards decarbonization and that kind of stuff. But to get to 10% of the world's energy, that means that we need some major export capacity in time. So we have people that are looking into this on our behalf, starting to look at pipeline routes and logistics and the metallurgy of building hydrogen capable pipelines. I think in the early years, assuming we can get going quickly, natural gas, LNG, will be a part of what flows down that line with a smaller amount of hydrogen. When it gets to the coast, methane has a higher boiling point than hydrogen. So when you basically do the same trick, cool it all off till you have liquid methane, what you have in the head gas space is hydrogen. And then you pull off that hydrogen and cool it further. So it can be a two-stage system that can do pure hydrogen or a mixture of the two and have two separate products going out. And then maybe 7 to 10 years from now, as more and more ships are able to handle liquid hydrogen. Right now, there's a huge fleet of underutilized natural gas ships, and not a lot. Hydrogen shipping by ocean is still in its infancy. It's growing. It's happening, but it's not at scale yet. And same thing with our hydrogen supply. We will need some time to ramp up. So it may be 7 to 10 years before we're exporting pure hydrogen, but that's the trajectory. I think building, however, 3 pipes at the same time is a good idea. So Norway, for example, is right now building a huge CO2 import terminal, and then they take the CO2 and inject it into an old oil field that's 100 kilometers offshore in the North Sea. So they expect the economics on CO2 import and sequestration to be hugely profitable. And Norway is good at making a lot of money. So I think there's probably something there, especially if carbon intensity does become a big factor in how governments tax various goods and things like that, which that's my prediction. So having one of these that's possibly going to be used later for CO2 imports to drag back, and like I say, we can do it through our process at extremely low cost. That's useful. Another thing is our process begins with an air separation unit. So we have not only oxygen to push in the ground, but we also have a source of nitrogen. Now, I'm not a big fan of ammonia pipelines because ammonia is a very dangerous product. If there's one spill on a big ammonia pipeline, everything in that valley could die. And I don't want to ever have that happen. So I'd rather have a line that we could just push nitrogen to the coast in one and hydrogen to another. So if international exports go more towards ammonia, and they're already taking ammonia shipments into Japan to make electricity and things like that from places like Saudi Arabia. If that becomes the growing trend, then at least we can make a whole bunch of ammonia at the coast right where it gets loaded into the ship. Or if it's not the case, then we can use the same line or all three lines just for pure hydrogen exports and liquid loading of liquid hydrogen. So that's the flexibility I like. And I think that it's, it'd be great for Canada, and it's really hard to be upset environmentally about a giant carbon negative hydrogen export source that has huge environmental benefits for the whole world, while also providing huge financial benefits for the Western Canadian economy. We've got an interesting advisory board. One thing that I think that gets lost in conversation a lot, like I've seen articles that suggest that 10 million people died in 2020 from air pollution. 10 million people, and there's only 7.8 billion of us. So in any given year, that means there's about a 1 in 700 chance that any one of us in any given year will die from air pollution. That's a total insane crisis level problem in our society, and we can save money while transitioning away from air pollution. So, that's one of my big motivations for this business, and why I want to see it proliferate so fast is because I think that it's, we have something that's raging, and it's way worse than the amount of deaths we had last year from COVID worldwide, and hardly anybody's talking about it. So personally, I'm not too worried if the ocean goes up a meter 100 years from now or down 100 years from now. My background is geology, so I know there's natural variation that's, even in the last 10,000 years, very, very significant. How much of an effect do we have on that? Do we have an effect? Yes, I think we do, but I don't think it's an emergency crisis, but air pollution absolutely is. So anyway, I'll move on to the next slide. This crisis will be solved in part by hydrogen. That's my firm belief. So I know there's a few questions that have popped up here.
Grant, thank you so much for that incredible presentation. We are excited to see where Proton will go in the future. But like you said, we have a number of questions, and we'll try to address as much of them as we can. The first question is from Mohammed. He asks, in situ combustion is a very complex process, from ability to retain the combustion process active. Any comments how the temperature bandwidth is managed, since the higher temperature can eat up the hydrogen produced, and also how the gas breakthrough is managed? And also another question, these are very technical questions. Any comments on downhole hydrogen filtration? Is this process commercially viable?
Sure, I'll start with the first one. So yes, the chemical reactions are complex. We know basically where the main temperature band for triggering water gas shift is based on a huge, enormous history of steam methane reforming. There's 100-year-old papers, maybe not 100, but probably 80-year-old academic papers on exactly these types of studies. So for a process engineer, Most process engineers are much more comfortable with steam methane reforming because they can predict the average reactions, the average compositions for a given temperature pressure band within a certain part of their pipe. So that can all be calculated with, these mathematical models that are actually pretty good. Even if it's not exactly how it physically happens, the net calculations are very predictable. When you have a giant heterogeneous rock chamber that's full of weird fluids and minerals and various things like that, changes in porosity from place to place, clay layers and shales and breccias and all these very complicating factors, you have to just kind of get started and optimize based on your results. So I think artificial intelligence, machine learning, these will come to bear. Initially it's going to be people looking at a graph going, oh, if we inject oxygen over a shorter cycle over here or a longer cycle, we notice that there's a bigger or better or shorter or worse bloom of hydrogen in our composition of our produced gas stream. So there's going to be a significant amount of optimization work, and it's mostly empirical optimization models as opposed to predictive simulation. You can go quite far, and I've seen some models. My background, I did a master's in reservoir characterization, and I've seen into the depths of reservoir simulation mathematically quite a bit. And I just don't believe, because one small error bar on a few different variables can cascade into outcomes to be whatever you really want. So I'm a firm believer in go to the world and optimize with real knobs and valves. And then, from there, we'll see what and it will vary by reservoir. Some are at different reservoir pressure. So the partial pressure of oxidation hasn't yet full oxidation or partial oxidation. There's enough complexity to it that I think that tuning the model with, eventually with AI, but initially with just, a spreadsheet is going to be much, much more important than predictive advanced models. Oh, and the second part of the question, filters work. We have tested them at surface to make sure that H2S doesn't poison them. We think that there's room for improvement. So far, we've just used commercial off the shelf, but we rented a warehouse in Calgary where we plan to start making our own, having different alloys, different designs for maximum surface area, low cost, and ease of installation and longevity. So within that framework, we need to, just keep optimizing until we have ones that we prefer. Like what's available today is economic, but there's optimization in all of this to improve.
Thank you. For our next question, I'm going to combine a couple of questions that we have received. And I know that Proton has a pilot site in Saskatchewan, so maybe you can provide us some insights for these two questions. One of them is, what kind of conversion rate are you seeing? Let's say, how much hydrogen are you producing from 1 barrel of in situ oil? And the other question that I thought it was along with it is, what fraction of energy is Proton providing to Canada now, or to Alberta or Saskatchewan?
Oh, okay. Right now, we don't provide a lot of energy into the economy. We expect this will change. We have a power purchase agreement with Sask Power that we plan to be up and running, well, as soon as we can. Looks like could still be within 2021, but it might slide into early next year with hydrogen compatible equipment. So there are many, many different manufacturers now that sell hydrogen compatible power production equipment, including Siemens, General Electric, Mitsubishi, Jenbacher, Rolls-Royce, and the list goes on and on and on for internal combustion, whether it's recip or turbine. Everybody's starting to install hydrogen compatible stuff. We expect to be a very significant part of the electrical supply, whether it's through fuel, and initially it might be fuel blending with natural gas and hydrogen. And as our supply expands, we think we'll be a much more significant fuel supplier for pure hydrogen equipment. And in terms of what we're producing right now is not very relevant. Our hydrogen production rate is not, it's not currently economic because we're just injecting air. Within the next 2 or 3 months, we will be trucking in liquid oxygen and injecting that, and that'll begin to bring us the data set that's more close to the Marguerite Lake data set, which was 55% oxygen within their blend and 45% nitrogen. I think that when we get sort of in the neighborhood of anywhere close to the results Marguerite Lake already demonstrated through enhanced oxygen, well, pure oxygen's ideal, but we'll be, beginning to truck out hydrogen. We'll probably have an announcement within about a month about small scale stuff that we're going to be doing in very short order, small scale though. And then later this year, we hope to be trucking out a few tons a day of hydrogen just as a compressed gas. There seems to be a lot of demand. There is a lot of demand. We're trying to figure out how we can install air separation units quicker because there's, with this carbon tax and escalation of the carbon tax, a lot of sectors of our economy are quite nervous about, their carbon footprint.
Yeah, for sure. So there's a follow-up question. Have you thought about using geothermal-like system to power your oxygen plant with heat energy from the oxidation reaction? With heat energy from the oxidation reactions in the reservoir?
Basically, if the more we cool off the reservoir, so yes, there is a lot of heat energy formed in the reservoir, but if we pulled it out to spin a steam turbine, for example, to make electricity, then that would be an opportunity cost for the same heat going towards driving hydrogen productive reactions. So I think that at end of life, once the fuel is all consumed, we will have a very nice geothermal hot rocks, hot water system that we can blow down energy from for another decade or two at the end of life, but we're not intending to in the near term. In terms of powering our air separation unit, we can use various sources of power. The cheapest, we believe, will be hydrogen through a turbine on site, but it is theoretically possible that if you co-located some wind or solar or geothermal from deeper zones, more of a pure play geothermal, then that's another way to power the air separation units, but it's not part of our baseline plan to do that.
Thank you. Another question is, are different kinds of underground oil and gas extraction processes utilizable for hydrogen production? For example, can systems like steam-assisted gravity drainage be reused for it?
Yeah, I think post-SAGD is ideal. You have a nice pad with like thermally cemented wells. You have usually an old pad has something going into it just for pressure support of adjacent productive pads. As your steam chamber cools and the steam collapses and condenses, then you have a pressure problem for building steam chambers adjacent because it becomes a thief zone for the other newer, more productive ones. So this works hand in hand very well with SAGD, especially on late life pads where we can, take full advantage. When wells are drilled into SAGD region, usually there's bottom water, not always, but usually in any case, there's rock below. And so there's always some amount of standoff above the bottom of a SAGD chamber, and all of that oil below the production pipes will never be produced by those production pipes. So with our process, it can become a fuel source, unswept areas, parts that had a difficult time making it to the reservoir become fuel for our process. And it's already high enough temperature that our thermal losses are less. And there's lots of steam in the system, which is one of the key ingredients for water gas shift. So post CSS, cyclic steam stimulation, post SAGD, I think those are extremely excellent pre-builds for us.
Thank you, Grant. We have another question that I am also interested in because I'm a pipeline engineer. The question is, hydrogen can cause embrittlement of steels and other metals. Will expensive specialty alloys be required for pipelines and other components to maintain safety?
It depends on partial pressure and metallurgy. Anything that was designed for H2S is generally okay for flowing hydrogen. there's a company in Calgary called GDM who just did a study about that. Some things yes, some things no, and some things kind of. If it's a low pressure system like residential distribution, the pipes can handle more hydrogen than the appliances. So you can get up to about 30% hydrogen until the appliances start to have problems. But because it's a low pressure system, the distribution pipelines are okay at that partial pressure of hydrogen. If you're in a big main line at high pressure, then that's where it starts to get more, you have to be more cautious how you approach it in terms of partial pressure of hydrogen. So I think we'll start to see very modest on the big export lines, very modest introduction of hydrogen. Like even if they started and said 0.3%, that's allowed now, and then monitor it for a while, have some tags hanging inside the lines and do a rigorous assessment as it builds out. I think they'll see that they can get to 10% or more without a problem, but it'll start conservative and slow. Many parts of Europe are already blending hydrogen into natural gas, and we will too.
Yeah, I believe there are a couple of projects already in place in Alberta from two different pipeline companies.
Yeah, so if it's no problem if you're an end of pipeline customer. For example, if there's one big pipeline going up to Fort McMurray and it's all just more or less getting burnt within steam generators, blending into that scenario doesn't require the permissions of everybody. But if you're on a big interconnect system, your hydrogen is going to end up in Chicago or California or wherever. So that's a much bigger challenge. You have to basically assess everyone to the burner tip, because some users of natural gas don't want any hydrogen. If the methane itself is a chemical feedstock to something, it causes hiccups and problems for them. So with so many cross-border regulatory bodies, I think things will start very conservative and very slow, and then we'll see where the pinch points are, and then up the level in time. I think that'll be a fast thing. A virtual hydrogen pipeline, you can liquefy it and put it on trucks much sooner, in my opinion.
Thank you, Grant. We do have many more interesting questions, but we are also running out of time. So I'd like to ask you, we'll send you these questions to you.
You can. I don't mind going over. Let me just check my schedule here. If you guys are okay with it, people can just, I've got a half hour. If people want to drop off the call because they have something to do, no problem for me. I'm happy to stick around and answer whatever questions come in to the best.
Okay, that's an option that the audience is given. I would like to ask them to raise their hands if they would like to stick here to get more questions answered. Okay, it seems there's some interest. Grant, do you mind if I just do my 5-minute presentation about ASME, who we are, and then we'll get back to continue with the questions? And thank you for your offer about staying here to answer more questions, because there are many. I think okay, so I will share my screen. I will not take much more of your time. It's only about 3 minutes of this presentation. I would like to share with the audience what is ASME, the Southern Alberta Section. So, because we are the ones who brought up this presentation to you today. And this is just a quick update about our section. So the ASME family has more than 100,000 members, and we are over 40,000 volunteers. The mission of ASME is to serve diverse global communities by advancing, disseminating, and applying engineering knowledge for improving the quality of life and communicating the excitement of engineering. The vision is to be an essential resource for mechanical engineers and other technical professionals throughout the world for solutions that benefit humankind. The Southern Alberta section has roughly 370 members, and if you look at the graphics, a vast majority of our members are above 50 years old, and what we would like to do is to encourage other members in the younger range to join us as well. This is a really good place to meet other people in the mechanical engineering industry. What is our value proposition? We always receive a monthly magazine which shares articles of the latest happenings in the industry. We have access to the ASME e-library that has thousands of texts with topics ranging from heat transfer to robotics and controls. We have instructor-based courses. And of course, you are always invited to join our chapter events. How can you get involved with ASME? First of all, tomorrow we have our next event, which is presented by the University of Calgary student section that is more focused towards younger engineers who are curious about the career of a project manager. And in the chat, you will see the link to that event. We are also looking for volunteers, and we are also welcoming technical presenters. So if anyone in the audience is interested in presenting another topic in the future with us, you can reach out to us by email. And we are also active on LinkedIn. That is possibly the fastest way to follow our updates. And we also have an ASME community page. All of that is being posted in the chat if anyone is interested in connecting with us. I will stop sharing now my screen and we will go back to questions. Thank you for your patience, everyone. Let me go to the next question. We have somebody who asked many questions, so I'm trying to figure out which one is. Let's start with this one. Costs and expenses to calculate cost of hydrogen per kilogram for SMR are relatively known and can be reasonably estimated. What numbers and/or assumptions did you use to calculate hydrogen cost using your technology?
Well, first off, our main assumption is that we have no other byproduct cost streams. So this model assumes we're not selling nitrogen, we're not making ammonia, and we're not getting a revenue stream from oil. Just on a standalone life cycle, not life cycle, what do they call that? Basically, if you include all the capital costs and the OPEX through time and average it out, then we think that a low levelized cost. We think we'll be at a levelized cost in the neighborhood of 25 cents at our first full-sized, 25 cents per kilogram at our first full-sized demonstration. If we're building many of these things, we expect that the cost structure will drop appreciably, and we see a pathway to getting eventually below 10 cents per kilogram.
Thank you. In the presentation, you showed that you will only produce pure hydrogen to the surface, but were you talking about co-injecting CO2 with oxygen? Did you mean co-injecting CO2 your process would generate or someone else's CO2?
We would use someone else's CO2. So the carbon tax is going up to $170 per ton by 2030 in Canada. And if somebody will pay us some portion of that to co-inject their CO2 into our stream, then that's an enormous opportunity. For example, one plant that does 10,000 tons a day of oxygen injection could also, with no extra energy costs, drag along 20,000 tons per day of CO2. And if the carbon tax is $170 per ton, 20,000 tons a day, that's worth looking at as a low-hanging fruit. How we entrain it is through a venturi, which is basically a gas jet pump that we can use the oxygen to cause a low pressure zone in the CO2 supply, and it basically sucks it in and entrains it into the same stream. So that can be further rewarmed with some of our waste heat to increase the pressure further. So we can dial up either the exit pressure of the mixture, or we can dial up the amount of the ratio of CO2 to oxygen that we put in. But given the giant economic target that's suddenly brought into existence by the federal government and acknowledged and sustained by our Supreme Court of Canada, I think that not contemplating that opportunity would be short-sighted.
Thank you. The next question is, if CO2 stays underground, do you need any technologies to carbonate it into rocks?
Yes. So one of the patents that we filed is about accelerating the inducement of carbonate formation. So there will always be a natural rate of carbonate formation within the reservoir, and a certain carrying capacity of dissolved ions that will react and trigger these carbonate forming reactions. However, if it's desirable to accelerate that for pressure control challenges or other volumetric types of constraints, then we can pack a lot more in the same reservoir by dumping in dissolved ions. A boiler blowdown water stream, for example, from SAGD is often has a pH of like 11 and a lot of dissolved ions. If we take that and put it into the bottom water where it's cooler and the carbonates preferentially precipitate first, we'll be plugging off the bottom water porosity with carbonates within the pore space. And that's something that is addressed within one of our patent applications.
Thank you, Grant. Another question is, where do you foresee assistance or technical support needed from the service sector?
That's a great question. So I think I highly recommend anybody who's in the fabrication business or support business, whether or not proton existed, hydrogen is definitely a huge part of the decarbonization requirement. So if you make valves, make sure that something in your lineup includes hydrogen compatible valves. If you make pipes, flow meters, pressure vessels, all of these types of things, I believe there will be a robust market, not only here, but an export market for hydrogen things going on overseas. Yeah, I would highly recommend try and refocus your venture in that way. Third-party evaluation of carbon intensity is going to be a suddenly needed service. And in terms of service sector, like a lot of the stuff that we use on a day-to-day basis at our field site is regular oil and gas service stuff. We drill the well. We often have service rigs showing up to do pump changes and fix stuff and replace tubing, install things. And then, welders, pipe fitters, all of that normal oil field stuff happens and is required. That expertise is required in our process too.
Thank you. We have other questions. What may be some potential issues that arise with installing hydrogen production systems in oil and gas extraction systems?
It depends. So if it's designed around H2S systems, there's not a whole lot of additional constraint or consideration in the most part for the oil handling side. A little bit of hydrogen will show up with the oil in the solution gas that comes with it. So if you have a completely sweet facility and system and you start doing our process in it, you're more likely to have challenges. So in that case, we would just use the physical surface footprint to basically start fresh. So this would be, for big, sweet, old Pinnacle reefs or, whatever. But in cases where there is H2S handling capability and equipment and pipe spec, the oil side more or less stays how it otherwise would be. The hydrogen side is all new anyway. So yes, you need to have hydrogen compatible pipes, welds, pumps, like that whole gas separation and handling side is new and specific for the purpose.
Mm-hmm. Can oxygen O2 be produced in other ways than removing from air?
That's a great question. So our future projects division has been doing some tests in that regard, some prototypes. That's a little bit of what we're doing at our warehouse in Calgary. Trying to find paths to drop the cost of air separation directly influences the cost of our eventual hydrogen production. So I won't elaborate on details yet, but I think it's definitely possible to dramatically improve the cost structure of oxygen production from air.
Thank you. Another question, what kind of purity of hydrogen does proton process produce? Fuel cell quality?
So the only thing that can dissolve through a palladium alloy is hydrogen. So yes, it comes down to how clean is the receptacle. If it's contaminated with some air, then you'll have some air in it. If it's, strongly cleaned and down to vacuum and then part of it's a volumetric game. Part of it is a pre-cleaning game, but fuel cells need very pure hydrogen. That's not our initial main consumer. People who are just burning hydrogen in a turbine don't need perfectly pure hydrogen. People who are just storing it don't need pure hydrogen. People who are co-mixing it with diesel in diesel internal combustion systems don't need pure hydrogen. So there's a lot of, you know, you can use a lot of SCSI hydrogen if you want. And definitely though, the premium market is in the fuel cells. For example, in California, people are paying like $12 a kilogram at retail stations, US, and it costs us about $3 a kilogram to truck liquid hydrogen from Saskatchewan to San Francisco. So there's a huge opportunity to capture some of that arbitrage.
Thank you. Next question. How would the technology be applied to gas wells?
It can be applied to gas wells. That's not our initial focus because a good gas reservoir depletes so much better than a good oil field. A good oil field still has a huge amount of oil in the ground when it's, you know, deemed done. And a good gas field, they might have already got 80% out of it. So the advantage with gas fields is a good gas field has convection, and that can be helpful. It also can be at extremely low pressure initially. But if you just look at the volumetric storage of a gas field versus an oil field, you have more gigajoules in liquid hydrocarbons than an equivalent volume of gaseous hydrocarbons. So there's my preference is to play more on the oil side initially. However, if you have a big air separation unit and a few wells around, we will be testing lots of different systems, including gas.
Well, I think we have addressed most of the questions, but I would like to close out with one that I think it's probably in many of our minds. Like overall, proton technology sounds like a win-win. So what is holding this technology back from becoming more mainstream? What do you think?
Cash. Yeah, I want more money so I can go build at large scale and do a big demo. So nothing's holding us back other than our financial resources.
Okay, thank you. Is there any closing remarks that you would like to share with the audience?
No, thanks for showing up and listening to me drone on and on about I consider exciting clean energy technology that I believe can revolutionize the Western Canadian economy, and especially in terms of our environmental performance and international palatability for goods we create here.
Yeah, I think overall we are excited about the technology that Proton is bringing, and we look forward to see how this develops, and we'll be watching you.
Great, thanks.
As a token of our appreciation, we would like to offer you donation to a charity of your choice, and we will follow up with you by email for this.
Oh, great, thanks. I'll tell you now. It's the Mars Society of Canada.
Mars Society of Canada?
Yeah.
Okay, well, with that, we thank you so much for your time and also for your extra time that was not original plan. I think we had wonderful discussions, and we will follow up with you about the recording. It will be available, and I think our guests are also interested in that. Thank you so much for joining us today, Grant.
Great, thank you. Bye for now.
Thank you.